Hello guys, and welcome to another video. This is probably one of the most requested videos from the Show Me community and people just out there. Would like to see something on the acid-base balance. So I had done one in the past. Wasn't very happy with it. Been teaching it a little bit differently. Just kind of wanted to come back and do another video with it, especially for my classes, for my Facebook page, just for a variety of places. So let's get ourselves started, and just to kind of set the pace and tone is we're talking about pH scale. And in the pH scale, remember, for a human body system, pH scale for the human fluids for our blood ranges between 7.35 pH to about 7.45 pH, just say on average 7.4. So there are two conditions that we're going to be interested in as we go through this. Is a condition called acidosis and a special type of condition called alkalosis. So let's just look at what these are in general. First, we'll go more in depth on these two here in a minute, and really I'm going to hit these more in depth momentarily. So if you're in acidosis, your pH is below that 7.35 pH, and if you're alkalosis, you're above that 7.45 pH range there. So a few things that we want to mention as we go through this is really just talk about pH, review the pH concept, and understand what pH is. So with that, we're going to do a quick graph and look and discuss the pH scale and just look at these numbers and what they mean for us and a variety of other things. So something I always want to kind of get ourselves started off with, if you understand that pH is dealing with hydrogen ion concentration. So if we ever deal with the concentration of hydrogen ions, those of you guys in my MP1 lecture know that hydrogen ion concentration, the concentration of hydrogen ions, is 10 to the negative pH. And what this basically tells us is, guys, that every single time I change a pH value, it is a tenfold change. If I go in whole numbers, it's a tenfold change. So let's think of it this way. If I were to say 10 to the 0, that would be a 1. So let's take 1 is not 1, but 1 is 1.0. In science, that decimal is always there, and you just cannot get away from that. So if I had a pH that equals 1, and wanted to know the concentration of hydrogen ions, just remember, guys, that I'd have that 1.0 here, and I'm going to move this decimal to the left in one direction, so it would be 0.1 moles per liter would be the hydrogen ion concentration there, and vice versa if it was. So that's just the pH tells you guys how many directions in the tens position you're moving that particular thing. The bigger the number, the lower the hydrogen ion concentration would be. And that's something very important for us to know. And I'm going to erase this basic thing. I'll leave the equation up. So what you've got is anything, guys, that is less than 7, these things are called acids. And we already probably generally memorized this at some point. And what's important to note here is that hydrogen ion concentration is greater than hydroxide OH minus concentration. So we would call anything an acid as a proton donor. And this is important if you're going to understand amino acid buffer systems, as whether or not the carboxylic acid groups, the amino groups, are going to grab up hydrogen ions or donate them. Now, anything, guys, above 7, of course, is referred to as a base. And what's important here is if I look at hydrogen ions, they are far less in concentration to an OH minus hydroxide ion, and these are referred to as proton acceptors. They will grab up protons from acids and help to neutralize those guys. So by far, this is just really kind of enough to give ourselves an idea here. This equation will tell us why is it important in the bicarbonate buffer system that I affect hydrogen ion concentrations to affect pH, and just understanding here will also help us understand that as well. So just a quick recap. So something I oftentimes kind of show my students is this diagram that would show a liquid and showing us that you would have OH minus and hydrogen ions would be equal in a neutral pH at 7, and if I add more hydrogen ions, I'm getting more and more acidic, and if I take away hydrogen ions, I may get more and more basic, especially in those cases. So that's something very useful for us to understand there as well. Now, something that we have to understand is that in the human body, the partial pressure of carbon dioxide gas is by far the most important thing that affects your acid-base balance. It's the most important factor influencing the pH balance of the human body and the etc. CO2 is a weak acid, and you may not understand necessarily how it's an acid, but let me show you how this is an acid. When carbon dioxide in the body accumulates through cellular respiration, it reacts with the water, and you are 2/3 water. And when this happens, there is a dissociation, or rather a formation of a chemical compound called H2CO3, which is carbonic acid. Now remember, an acid is anything that increases hydrogen ion concentration, and this carbonic acid will dissociate into two ions, a hydrogen ion and then an ion sorry, I wrote the C there by mistake, didn't mean to do that, HCO3 minus, which is a bicarbonate ion. So this is bicarbonate ion. Now, what I always want to make sure, if you look at this chemical reaction, is happening in blood, in the fluids in the blood, but what I really want to show you as well is the physiology behind this. Is if you kind of imagine this side of the reaction, we have our lungs, and on this side of the chemical reaction, we have our kidneys. And these two organs are going to be constantly balancing gains and losses on this side of each side of these equations. For example, lungs, by either increasing or decreasing your respiratory rate, will actually affect the amount of CO2 accumulation or removal in the body. And then the kidneys can excrete more hydrogen ions or reclaim more hydrogen ions or excrete bicarbonate or retain or accumulate more bicarbonate ions, even go to the point of making bicarbonate ions in the kidney. So what's going to happen is each of these organs affect both sides of these equations. And something that is crucial to really understanding this, if you guys remember back in Chapter 2, for some of you guys heavy for A&P 1, know that this is an example of what's called an equilibrium equation. And anytime that I go on an equilibrium equation, and for example, I raise something on one side, it always shifts that equation towards the other side to balance it out. If I decrease the level of something, it will shift the equation that way. So if, for example, guys, in the body, if I hold my breath and I increase the amount of CO2, what I'm going to have to do here is I will begin to increase the amount of hydrogen ions produced, as well as bicarbonate, of course. But hydrogen ions are big here because what they will do is go out in the body and wreak havoc, damaging tissues, breaking apart the proteins, damaging secondary, tertiary, quaternary structures of proteins, etc. Bicarbonate is a weak base, and it also will affect strongly your acid-base balance. So what you'll see is the same thing can go on here, is the kidneys can adjust the gains and losses and shift these equations. So for example, if I have too many hydrogen ions and I end up dropping that, my body may shift breathing rate, for example, to accommodate for an increase of hydrogen ions. My breathing rate will go up, and so I can try to breathe out more of that CO2. My kidneys will respond by urinating more hydrogen ions and reclaiming more bicarbonates. And so these are just kinds of things that if you understand the basic physiology behind the respiratory system and the renal system and how parts in the kidneys we saw got rid of hydrogen ions in the urinary system, then that's something that you would find very useful there. Now, secondly, what we're going to start looking at is a very important relationship here that we have to fully grasp. And it's going to be kind of coming back to this, and I'm going to use another page, is this idea that if I ever see an increase in carbon dioxide levels, I must always decrease the pH. Why? I'm going to an increase in CO2 creates, guys, an increase in hydrogen ions. An increase in hydrogen ions means a lower pH. And if CO2 ever goes down, the pH must go up. These are inversely proportional. This, of course, means acidic. And this, of course, means basic pH. So let me kind of show you guys an easy model to try to grasp. If we got our balance, and remember, way back in chapter 1, something I always emphasize to you guys is balance is key. We have our CO2 and our pH levels. I'm going to need to make that a little bit bigger here. And so we have our carbon dioxide levels, and we have our pH levels. And given that, let's say, for example, my CO2 goes up, right? If CO2 were to have an increase, then, of course, the pH goes down like a teeter-totter, and vice versa, guys. If CO2 goes down, then the pH must go up. And this is a very crucial relationship to understand here as we get ourselves into some of the diseases. So what we're going to be looking at is two basic kinds of diseases dealing with this, and that goes back to that acidosis alkalosis. Is a respiratory acidosis alkalosis and a metabolic acidosis alkalosis. If something goes wrong with your breathing, then it's a respiratory acid-base balance issue, and if something is wrong with your metabolism, then it's a metabolic issue. That's as simple as that. But let's get down and understand that. And of course, to really first, we're going to look at respiratory acidosis. Now, to understand this, we need to be thinking lungs. So remember, we got carbon dioxide reacts with water. I need to erase that and start over. I'm having the hardest time with my newer stylus and a few other things here. So what's going to happen is, of course, guys, we make H2CO3 carbonic acid, which then dissociates into hydrogen ions plus bicarbonate ion. And remember, right here, you have lungs influencing what's going on here. And on this side of the equation, we have the urinary system and kidneys. So what we're going to begin to see here is a respiratory acidosis. Anytime you have impaired respiration, this could be to COPD, emphysema, asthma. Something here, guys, is causing my breathing, a low breathing rate, hypoventilation, neurological conditions, infections, things that are going to prevent you from being able to breathe effectively, to get CO2 out of the body. So what you've got here is an accumulation of CO2 due to the causes, guys. The cause here is a reduced respiratory rate. Hypoventilation is the number one cause, and CO2 builds up. So RAD would be cause. And then, so what's happening is this shifts our equation, causing a rise in the hydrogen ion concentration. And so we'll bicarbonate because these two guys go hand in glove. Now, the thing with this is that bicarbonates, it becomes a disease when this amount of hydrogen ions here can actually overcome the buffer system. Normally, the equal amounts of bicarbonate to hydrogen ions annihilate each other and they just get breathed out. But if something by far you end up getting the hydrogen ions go off and they begin to overcome this and the acidosis, that's when the disease happens, when the buffer is overcome. And it's when the hydrogen ions are not able to be taken care of. So what you've got is two kinds of responses, two kinds of what we refer to, guys, as compensation. Is respiratory compensation versus renal compensation. Now, respiratory compensation, if the cause here, guys, is a lowered respiratory rate, then the opposite is going to fix it, and we would increase our respiratory rate. And what that increase of respiratory rate is going to be able to do is pull out CO2 from the body, trying to remove CO2 as much as we can. Now, another thing is the kidneys are going to do is going to take these hydrogen ions and pull them out, and it's going to produce more bicarbonate. Now, what this is going to begin to do is, guys, is increasing the pH a little bit. And that's going to fix that. And then other buffer systems, for example, the protein buffer systems, are going to grab up hydrogen ions as well. So this is a really big kind of thing with that. Now, what we're then going to do is take a look at the other type of respiratory disease, and that is called a respiratory alkalosis. And with respiratory alkalosis, we're going to start with the same thing here. But first off, let's look at respiratory alkalosis. And so I'm using a new stylus. I'm just not very used to it. So with this alkalosis, remember we got carbon dioxide reacts with water, forming carbonic acid, H2CO3, which dissociates into H plus and HCO3 minus ions. And of course we have our lungs here on this side of the equation. We have our kidneys on this side of the equation. And let's look at the causes. Here, guys, in respiratory alkalosis, you could have a patient, let's say they are hyperventilating. They're having a panic attack, and they have an incredibly high respiratory rate. And this high respiratory rate is really beginning to pull this CO2 levels out of the body. And by doing so, this is actually causing an increase in the pH, right? So what you're going to do is end up having a lot more of the bicarbonates in the body, etc., right? So this is shifting that equation more towards, so you're going to be having an opposite shifts, pulling it back. So you're withdrawing the hydrogen ions really from the body, making it to alkalines, what's happening. So the rise in pH. So what's going to happen here is first off, with the respiratory rate, we just need to get the respiratory rate down. Now, this could be a result if you're having a panic attack, getting somebody calmed down, etc. allowing CO2 to build up. They're having a panic attack. You can have them breathe into a bag, and then their CO2 levels will begin to increase. Hydrogen ions will begin to build back up again, and then they'll be back into balance. Now, the other thing is our kidneys can take and put hydrogen ions into the body fluids and take this bicarbonate and pull it out, which is what's going to help to overall, guys, lower our pH as well. This is going to be the overall function of this, is to lower it, get it back to more acidity. And that should be a little bit easier to understand there once we get that guy. Once we understand respiratory, metabolic isn't really that concerning for us. Now, with metabolic issues, once we got this guy, metabolic should be easy to understand. And a metabolic acidosis, and again, we're going to have this acidosis, low pH, lower pH. So remember, we have carbon dioxide reacts with water, which disassociates into, or rather produces, for that matter, H2CO3, which also, this is what disassociates into the hydrogen ions and the HCO3 minus. And this is pretty important that we get, of course, you know what organs really help regulate which side of which equation. Is very important to get, grasp, and understand it, not just memorize our way through it. So, in metabolic, remember, we have impaired metabolic stuff. You get fixed organic acids, both accumulate and overwhelm this system. Let's say somebody is diabetic and they get diabetic ketoacidosis. Let's say they are doing extreme and intense exercises and produces lactic acid. These are acids which are lowering our pH, right? This is a lower pH due to metabolism. Now, the lungs are not going on, but there's been an increase in hydrogen ions here. Now, given that, the equation could shift this way. And one of the things that will happen in someone in acidosis is you will begin to see an increase here, guys, in a patient with this is an increase in respiratory rate. Now, this is what I always have to make the point of with students, is let's say you have a patient and they are hyperventilating. They are sitting there and you say, well, breathe in this bag. You might kill them. What if they are doing respiratory compensation from metabolic acidosis? This increase in respiratory rate will pull the CO2 out, which means it's pulling the hydrogen ions out of the body, leaving behind more bicarbonate, which is going to ultimately increase the pH back to normal. So on the breathing side, that's pretty easy. Now it's acidosis, so you want to pull out hydrogen ions and push in more bicarbonates. And then, of course, other buffer systems would accept hydrogen ions. So pretty easy there. Now, the last one that we look at is metabolic alkalosis. And then I'm going to come back and give you guys a few little special ones here as well. So, metabolic alkalosis, what we would have here is this overall overarching idea here is if we're alkalosis that we have an increase in pH. So CO2 reacts with water. We produce carbonic acid, H2CO3, which disassociates into hydrogen ions, HCO3 minus bicarbonate. Remember, our lungs. This is always so crucial to understand this from a physiology standpoint, and our kidneys. Now, in alkalosis, we are going to have, guys, an increase in the bicarbonate ions. Now, given that increase in the bicarbonate ions, one thing that we got to be able to do here is remember this guy he goes off. He isn't doing things. It's these guys here that we're primarily affecting. So what I've got to do is increase these hydrogen ions. So the overall response that we're going to have is that I'm going to lower my CO2. So lower my breathing rate, which is going to raise up my CO2. Mr. Lover just said something a little bit silly there. I don't know why I just said that. But as I'm going through that, I actually meant to tell you guys the reason why it happens. Let's say you get sick, you get a flu bug, stomach bug, and you vomit. And this vomiting results in a severe loss in hydrogen ions through the vomit. Your body pulls those off, lowering of hydrogen ions, a high increase now of bicarbonate. And what we're going to see is the response is a decrease in respiratory rate, which will allow a buildup of CO2 to help increase those hydrogen ions. It's going to help accumulate that. Now, once we decrease the respiratory rate, guys, remember we're going to now decrease that pH level back to acidosis. So we're back closer in normal. We're moving back more acidic, getting it back not towards acidosis, but you can tell that usually longer videos. So I think I'm starting to lose some of my concentration and focus on that. It looks like so. What I wanted to do as well here is we'll come in and look at some of these in a minute. Let me give you guys one little thing, a little table that I wanted to mention to help you guys learn this a little bit easier. And the mnemonic I want to give you is the mnemonic Rome. And in Rome, respiratory is opposite, metabolic is equal. Let's help you guys understand that. So we've got the diseases over here, and I'm going to abbreviate these 4 diseases. So there's respiratory acidosis, respiratory alkalosis, metabolic acidosis, and metabolic alkalosis. And I had to abbreviate those. And what we're going to take a look at with this Rome is 3 things. We're going to look at our pH. We're going to look at our partial pressure of carbon dioxide and our levels of bicarbonate ions. Now, in Rome, respiratory is opposite. If CO2 goes up, pH must go down. Let's use red here. If CO2 goes up, pH must go down. Now, normally, you're going to see a normal bicarbonate in respiratory. So, if CO2 goes down, pH goes up. Now, in terms of alkalosis, CO2 is relatively normal, but metabolic is equal. If the bicarbonate goes down, so does the pH. And if bicarbonate goes up, so does the pH. So Rome, respiratory opposite, dealing with pH and carbon dioxide. Metabolic is equal, dealing with pH and bicarbonate. And this is always a very useful thing when trying to do these particular types of problems. So here we have a 75-year-old COPD patient. And I know what you're already beginning to think. COPD, not enough oxygen getting to and from the lungs. We're already thinking a respiratory disease. Well, let's take a look. He's got an elevated CO2 level, which means, guys, remember, if CO2 goes up, pH must go down. We're already thinking respiratory acidosis, right? Respiratory acidosis. The why is that is, guys, CO2. His CO2 levels are up. That's pretty easy to get there. And with this guy, with his elevated CO2 levels, what would you expect to see with him? And let's take a look at respiratory acidosis. The cause here, guys, with respiratory acidosis is an increase in CO2. So we want to see this guy, he's going to try to breathe harder in blue to try to help accommodate for this, and his kidneys are going to try to get rid of the hydrogen ions, right? And that's what we're trying to do there in Mr. Herbert. Now, in this patient, we have Carrie, who's an anatomy and physiology student, who's having a panic attack. She's afraid of her final, which is tonight for some of you guys, and she's hyperventilating. Her heart's beating like crazy. She feels bad, so her mother takes her in. Her pH is 7.52. So obviously she's hyperventilating. We're thinking a respiratory disorder, and 7.52 is definitely out of this little range Mr. Lefford showed you here, right? That is definitely rather above 7.45. So we're already thinking alkalosis and lungs are involved. So we're already thinking respiratory alkalosis. Her CO2 levels are definitely below the reference range. So a low CO2 level, so caused by what? We're beginning to see a low CO2 level. This is opposite to Herbert, so respiratory alkalosis seems pretty good here. And this bicarbonate is right there in that range. But let's think about that. Bicarbonate is normal in a respiratory acid-base disorder, so nothing weird there. So we're looking at respiratory alkalosis. Why is that? Because, guys, she's breathing so fast, she's removing her CO2 from her bloodstream, making it more basic, but we should not be surprised at this level here remaining normal, given our Rome mnemonic. And what we would see from this young lady with a respiratory alkalosis is she's going to be pulling out those hydrogen ions, pushing in hydrogen ions to her urine, etc. So, and the last one is a 4-week-old baby who is very ill named Jackson. And Jackson has been vomiting for several days. In multiple days he's been vomiting. His pH is 7.5. We're already looking at that, going alkalosis. The vomiting is making us think, okay, but let's just see. Bicarbonate is definitely above this level. So metabolic, okay. So the pH has gone up and the bicarbonate has gone up. We're thinking metabolic alkalosis just from that. Vomiting, he's removed all of his hydrogen ions. Too many bicarbonates. So little Jackson's body with metabolic alkalosis going down is going to start breathing slower to allow CO2 to accumulate. His kidneys are going to excrete bicarbonates, and he's going to start trying to add hydrogen ions to the blood in little Jackson as well in the hospital. The medical staff's going to help him. So I really hope you guys find this Rome chart very useful in terms of getting this down and in your head. So guys, this concludes my video on respiratory and metabolic acid-base disorders on acid-base balance. Hope you find these videos helpful. Give me some good hints of things you'd like to see in the future. Email me through the Show Me portal. Find me on Facebook through Human Anatomy and Physiology Education in East State for Northeast State Community College. And guys, have a great day. I really hope to hear back from some of you with any great ideas. Thank you, and thanks for watching.